Chapter 6, Bending, Part C, Derivation of shear and moment from loading function. Example 1. Just consider we have a cantilever beam AB, which is fixed at A and free at B, and a concentrated load of P applied at free end B. We want to know what we want to draw shear and moment diagram. So RA is equal to the amount of force which applied at the other side, so that's P, and there is no other vertical forces, so these two should cancel out each other. And there is a counterclockwise due to the concentrated load at free end B, and that's MA is equal to PL, and the direction is counterclockwise. Mhm. If you want to draw the shear diagram, you just come up by the amount of RA, which is P, and as you travel to the other side, right side, there is no force to contradict you, and all of a sudden at B there is a downward step with the amount of concentrated load of P. And at the same time, if we want to plot the moment diagram, we easily know there is no moment at free end B, so that should be zero. And if we draw the moment, it just gives us a linear variation from 0 to all the way. The area under shear is the change in moment, so this height is P times L. We already calculated that MA is PL. Mhm. An interesting part is that as you move down, for example, here there is no loading from when you travel from A to B, there is no nothing in between. So in that sense, V shear diagram is a constant line. Mhm. And if shear is constant, moment should be 1 degree higher. So that's a linear. Mhm. So if one can say there is no nothing here, this is a 0 degree, which is a constant line. And if this is a 0 degree, this is linear. That's a 1 degree. And you can easily follow up that no loading is no nothing. Then it just comes to a constant line, which is you can call it 0 degree, and a high 1 degree higher, it's a linear, and that's a 1 degree. That's how we can approach the shear and moment diagram. Mhm. To from the easiest to the toughest. Let's observe the same beam with the effect of if we just have only a moment at free end B. So a single moment is in a such way that you can have it in any part of you can replace it at any part along all over the beam. So the same amount of moment, it just applies to, that's the point. The same amount of moment, it's applied to the support A. Mhm. Because there is no forces to be cancelled out, shear diagram is simply there is no shear. Mhm. And for moment, mhm, there is the same amount of M naught, mhm, at the beginning, no nothing to contradict. At the end, again, there is the same amount of moment. So that's the area under moment. Because there is no load, we have no shear. Mhm. And that's the shear and moment for the same cantilever beam by just having a single moment at free end. And let's consider the other situation which we have the same beam but this time happen to handle a distributed load of W. So in that case, if we have AB, a cantilever beam again, uh, handling a distributed load of W. So definitely there is a moment at A which should be cancelled out with the effect of the distributed loading. So if you do so, it just gives you a counterclockwise a half of WL squared. That's the amount of W. Mhm. And RA is again RA should equal to WL. Mhm. And how we can get this moment is just uh, convert the distributed load to a concentrate of WL and replace it at the center, and then sigma MA equal to sigma MA. By developing the moment equation, you can easily get the moment at A. So it's not zero, that's MA, mhm, a positive MA minus A should be equal to zero. And that just simply gives you MA is a half of WL squared. And if you draw the shear, it just gives you a just come up with the amount of load. There is no nothing at free end, so it just decreasing to the support in terms of shear. And again, for moment, there is no moment at free end likewise, and it just goes all the way down to reach the amount of MA, which is a half of WL squared. And this is a parabolic spandrel second degree. Hmm? And let's make it a bit cleaner. Do you remember we talk about if there is a constant load, we do have a 1 degree in shear and second degree in moment. If there was no nothing here, it just goes by a constant line for shear and a linear or first degree for moment. But if we do have a constant loading, it just goes by a 1 degree for shear and second degree for a moment. And let's see what's the point of this is a parabolic spandrel. Spandrel is if by the function of y is equal to a constant times x squared. Then our area is if it's squared, it's b times h over 3, and centroid is b over 4. And if you have the same kind of shape, parabolic spandrel with the higher degrees, but with the same uh, geometric shape. If its y is equal to again a k times x to the power of n. Area is b times h, so this is our b and this is our h over a n plus 1 for area and n plus 2 for centroid. So if n plus 1 for area and n plus 2 for centroid, if k is equal x equal to 2, 2 plus 2 is L over 4 is the distance of centroid to the closer support. And definitely the other is a 3/4. This is 1/4, the other part is a 3/4. And if it was higher, uh, you can go with the higher degree. Again, if you don't want to do the mass, area under shear, which this one is WL, is equal to amount of moment. So that's a half of WL squared area under here. The reason it just goes down, that's due to the fact that this is a negative bending. We'll talk about that soon. Thank you.